Well, thank you to the organizers for inviting me, and it's really nice to be back in Vienna again. And thank you all of you for showing up, because I'm sure you're jet lagged. Many of you are, just like me. Okay, so this is going to be mostly joint work with Peter Cholak and Charles McCoy, which we started actually the spring of my first year there when Charlie was on sabbatical and he was visiting Notre Dame. And we're going to talk about big Ramsey degrees and computability theory, mostly of Henson graphs. So a little bit of review. Here are our two most well-known and loved Ramsey theorems. The finite one and the infinite one. And the finite one is looking for finite objects colored inside of another finite object. And you're looking for some finite object big enough so that you can get down to one color, right? And the infinite one, you're coloring finite objects inside an infinite object, and you're trying to get down to one color in another infinite object. So there are analogs of these for structures, and the finite one is coloring finite structures inside finite structures, and the infinite one is coloring finite structures inside an infinite structure. We call this second one finite dimensional because the thing being colored is finite, and there's also infinite dimensional, which leads into topological Ramsey spaces, which I am not talking about today. Okay, so definitions, finite structural Ramsey theory, very general. If you have structures A and B, and A embeds into B, which is our less or equal notation there, as a induced substructure, then we'll let B choose A denote the set of copies of A inside of B. Some people use embeddings. It doesn't matter. You just multiply by the number of ways you can order or embed something into another thing, right? So it's all the same in terms of results. And then a class K of finite structures. So think finite linear orders, finite graphs, finite ordered graphs, is going to have the Ramsey property if given any A and B in your collection, there's another C in your collection that's so large and maybe so complex that you're going to be able to get this Ramsey theorem. So coloring your copies of A into C into R colors, you can find a copy of B and C in which the copies of A have the same color. Okay, so lots of work done. So I mentioned finite linear orders, that is Ramsey's theorem. Finite ordered graphs, that is due to Nash-Troll and Riddle, and also Abramson and Harrington. If you take the order away, then you get something called small Ramsey degrees, which still you can get down to a finite number of colors, which is only dependent on A, but not necessarily one color if you take the order away. Okay. And then also Nash-Troll and Riddle did this whole slew of work in the 70s, which got built on since then, currently even being worked on, about which Freisey classes have the Ramsey property. And included in this paper are finite k-click free graphs for each k, as long as they're ordered. So in 2005, Kekkers, Pestov, and Todorcevich showed that the Ramsey property for Freisey classes is linked with extreme amenability of the automorphism group of its Freisey limit. So for instance, think class K being finite linear orders, then this big bold K is the rationals. Or if K is finite linearly ordered graphs, this big K is the random graph with the rational ordering on it. Then in terms of finite dimensional Ramsey theory, we usually can't get down to one color for copies of a given structure, but we can often, or the question is, when can you get down to finitely many colors? And then the second question is, how do you actually characterize that number? And so the definition, this general definition comes from the KPT paper, but there were previous works on the rationals prior to this paper, and we say that K has finite big Ramsey degrees if for each member of your class of finite structures, there's some number bound, so that whenever you take a number of colors of your copies of the finite structure and the infinite structure, you can find a copy of the infinite structure so that you have no more than T colors. So if T is 1, then you have the Ramsey theorem, essentially, for this structure. Right? And most of the time, if you have some nice enough structures, you're going to get the Ramsey property for vertex colorings, but usually not for structures of size 2 or more. So the big Ramsey degree, if it exists, is defined to be the least such T so that this Ramsey property holds. So back in, the 2000s, by 2006, the big Ramsey degrees of the radograph had been classified. And it was but the question was like, what are they, right? What are they? Why do these mysterious extra numbers pop up? Why don't they exist when you're in the finite case? And what we know by now, after a lot of people have done a lot of work, is that the big Ramsey degrees are really about trying to find the optimal structural expansion of your class so that the Ramsey's theorem does hold for that expansion. And where does that expansion come from? It's induced from linearly ordering your structure in order type omega. And so simple, right? So you structure the rationals in order type omega. You get Sierpinski's coloring for pairs, where you color the pair blue if the two orders agree, you color them red if they disagree. Every substructure that's, again, a dense linear order is going to retain both colors. But also, you can always get down to 2 colors. So that linear order, that well order in terms of order type omega, as opposed to the order on the structure, together are classifying the big Ramsey degrees. Okay, so I'm going to give you a couple of examples to hold on to. So I've given talks where I give the whole big broad picture. I am not doing that today. You can look at other slides if you want that. I'm just going to stick with rationals, radograph, and Henson graphs. So the rationals we think of as a dense linear order, not topologically here. That's a different area of work, but related. The big Ramsey degrees of the rationals are characterized by the diagonal antichains in this tree. So what's going on here? Okay, originally, when Devlin was working on this, and Laver was working on this before Devlin, they thought, okay, let's just look at the tree of 2 less than omega, use the lexicographic order, that's the rationals. Okay, let's try to get some Ramsey theory on there. In hindsight, you can use the theorem of Millikan to get it. They didn't have that at the time, but they did it similarly in some sense. And in this tree, once you have this copy of the rationals, you can then take a subtree where each level of the subtree has at most 1 terminal node. The terminal nodes are giving you another copy of the rationals. And within that copy, these are the substructures, the expansion structures that are determining your big Ramsey degrees. So for the big Ramsey degree for coloring pairs of rationals, you have 2 expanded structures, just these little trees here. And the green nodes are denoting rationals, and the black is just denoting the tree structure. Okay. For triples, you can imagine, they're called Joyce trees, if you've heard of those. For triples, you can have 16 different non-isomorphic subtrees, which are all diagonal antichains, which means they're antichains. Their splitting degree is 2, and each level has at most either 1 split or 1 terminal node, never both. And that's a diagonal antichain. And so this expanded tree structure with this extra linear ordering in order type omega or some finite linear order is giving you the big Ramsey structure from which we deduce these. And then for, this is very live, for the radograph, Sauer was, well, he worked with Erdős a lot. So he knew this other work of Erdős, which took the edge-non-edge relation of an ordered graph, and it induces then a tree structure, which again is 2 to the less than omega. And so inside 2 to the less than omega, going right is going to mark that you have an edge between these 2 nodes. So these 2 are going to also represent edges, or K2. And these 2 are going to represent non-edges, so the complement of K2. And these are the big Ramsey degrees, or the structural expansions that give you the exact Ramsey property for edges and non-edges in the radograph. And then for paths of length 3, you're going to have a lot more, but I've just drawn a couple of them so you have the idea of what's going on. Okay. So main points, these are what diagonal anti-chains look like. These are the structural expansions, right? So you expand your language using a tree structure, a meet, a left, a right, you know, the lex order on the tree. And then for here, we have edge and non-edge relations as well, embedded in the structure. And these are completely characterizing the big Ramsey degrees. So if you fix one of these, what we now call diaries, and you take all of the copies of them in the expanded structure, you have the Ramsey property. And then the big Ramsey degree is just about counting them up. Okay, then triangle-free Henson graphs. These are the graphs on omega many vertices, which have no triangles. They embed every finite triangle-free graph, so they're universal. By default, they will also embed every countably infinite triangle-free graph. And then they're also homogeneous, which means that if you have an isomorphism between any 2 finite subgraphs of it, it can be expanded to an automorphism of the whole structure. Equivalently, the Henson graph is defined by this extension property, which is similar to the extension property that defines the radograph, except, well, you can't have any triangles. So given any finite pair of disjoint pair of vertices, disjoint sets of finite vertices, where F has no edges in it, then you can find another vertex in your graph that has edges with every vertex in F and none with G. And if you do this, if you list out all your finite subsets of omega, which are disjoint, do this extension property on it, build a graph, you will get a Henson graph. So this makes it really nice because you can build these things computably in any sort of manner that you want to, and you know, the world's your oyster. Okay, so a particular way of enumerating the triangle-free Henson graph in order to reduce a priori the number of different possible ways you could expand the structure is to put an edge between each 2 adjacent vertices there. So that has the effect of taking you off of the leftmost path here. And we're going to use this particular enumeration in our work on the computability theory side of things. So this is the visual representation of an enumerated triangle-free Henson graph. This is the tree of 1 types where you have particular nodes that represent these vertices. And having the picture in mind makes things a lot simpler. So when I worked on things in set theory, this is how I did them, you know, did some forcing on these things. When we work on computability theory, Peter doesn't really want to not mention the trees because he wants everything as simple as possible. So this is the picture, but then we actually just do everything graph-wise without the tree of 1 types. But it's always there in the background. So some preambles, theorems, they have finite big Ramsey degrees, and we know exactly how to characterize them. So building on the previous 2 examples, we have the expansion to include a tree structure and a linear ordering. We have diagonal anti-chains and these pathing numbers, which are giving you edge non-edge relation. But when you have forbidden k-cliques or n-cliques, it so happens that every subgraph of that, which is again a Henson graph, is going to retain the leftmost path because you can't have a copy of the Henson graph in finitely many types or neighborhoods. So this gives an extra bit of information that we have to encode. And then also because we have some forbidden configurations, initial bits of those forbidden configurations need to be noted because they are what prevent you from extending to a full copy of the Henson graph. So they come into play in the characterization of the big Ramsey degrees. And then this is something that's a little funky, but you get used to it. It just says that if you have a node which is going to represent a vertex in your minimal copy, then you need to kind of minimize everything else as it goes past. So here are some diaries for the triangle-free Henson graph. Here's an edge. This one's passing by this one. The brown is the leftmost path, which means if you're on here, you have no edges with anything. And this leftmost path is retained in every subcopy of H3, which is very different from how the Rado graph works or the rationals work. But still, the big Ramsey degree for the pairs is still 2, but for the non-pairs, it grows really, really fast. I mean, non-edges, it grows really fast as this n goes up. So what's different? For the non-edges, they might come off of the same stem, off of here, whereas the edges can't possibly do that because once you're over here, you've already coded an edge with a vertex, and therefore no nodes in these neighborhoods can have edges with each other. Okay. Then if you're over here, and they come off at different places, you can still add edges with a common vertex at that level. And so this is what we're calling coding node gadgets. That was number 4. And it's a way of minimizing what can be added up here in relationship to this node. Okay, so all this to say, there's a bunch of extra stuff that goes into the pot when you have big Ramsey degrees of triangle-free or 4-clique-free graphs versus the Rado graph. And this is going to jump up our complexity in terms of what we can encode in these graphs from the Ramsey property. Okay, yeah. So this is kind of hidden in there. These sorts of things are relevant. Okay, n-clique-free Henson graphs are the analog, but now we can't have any copies of Kn inside. And they're also defined by an extension property where now one of the set of vertices needs to not have any copy of Kn minus 1, and then you add a vertex connected to everything in F and nothing in G, and that's how you can build it. All right, so we have finite big Ramsey degrees for these things. This is an extension of this theorem to many more structures. Proof slightly different in the sense that it's quicker, but the bounds are higher. And then we have these exact characterizations. We actually have exact characterizations for these, but I'm just stating this. So now, this conference. So that was preamble. Jockish colorings. Okay, so these are really, I'm sure you're all familiar with these. It's probably old hat to you. These are really cool. So Jockish showed that if you color the n tuples of the natural numbers by this JN coloring, which is a computable coloring, then any homogeneous set is going to compute the n-2 jump. Okay, so we are going to use these, and we're going to try to use the information about these tree-like structures that encode the Henson graphs to get our big Ramsey degree results in computability theory. So the Jockish coloring is initially using triples, and you define it to be 1 if these two approximations to Ks, Kt, and X with some oracle is 0. Otherwise, I mean, if these aren't equal, it's 0. And this is computable in X. What? Okay, so K is the halting set, X is the oracle, and S is the amount of information you're allowed to use. I mean, the number of steps. So inductively, we can define jxi plus 1 from jx prime I, and then for each k, these colorings will be x computable. We'll iteratively define an x computable coloring jx3 plus k from jxk3. And the upshot of all of this is that we get these nice colorings, which are given to you in terms of products of the previous ones. So they're encoding all of these jumps in terms of if you go down in the length. For us, we're going to, I think today, mostly just use X as the empty set. So we write JN. And so these are the colorings that we're using. Okay, so a long time ago, well, a decade ago, I presented some computability problems because I knew enough to get other people into trouble. And the upshot of that was some work in 2020 that led to this AMS memoirs of Angles, Doriak, Cholak, Chafarov, Monin, and Pate, where they answered a whole bunch of the questions, and then also laid the groundwork for a lot of more work that could be done. So in that memoirs, some of the theorems they proved were the following: the Halpern-Loikley theorem, which is a Ramsey theorem for trees, which has been the pigeonhole principle for the Millikan theorem, which has been the Ramsey theorem used to get big Ramsey degrees for the radograph and things like it. That theorem is provable in RCA naught. Or in other words, if you have a computable tree and a computable coloring, you can get a computable instance of the Halpern-Loikley theorem, which I thought was really weird because the Halpern-Loikley theorem is much harder to prove than Ramsey's theorem. But in terms of computability theory, it's not. So the degrees that go up with this is when you do the induction to get the Millikan theorem at different levels at the same time. They also showed that the big Ramsey degree theorems for the rationals in the radograph are provable in ACA naught. Really, what they did was they showed that big Ramsey degree theorems for pairs in here are going to compute 0 prime, and then you get this from that. They showed that there's a computable coloring of pairs for rationals, triples for rationals, pairs for radograph. There's a computable coloring of pairs of rationals, all of whose subcopies are going to compute 0 prime, but the big Ramsey degrees for the radograph has cone avoidance for pairs, which is kind of weird. Okay, now Henson graphs. So this was 86, this was 89. They proved that the triangle-free Henson graph is indivisible, which means that if you have a vertex coloring on it into finitely many colors, you can always find a subcopy that has one color. So Komiat and Rudel did triangle-free, and Elzahar and Sauer did all ends. From this, so I don't know how old this lemma is, but anyone who thinks about it can really come up with it. So modern folklore. Given a computable coloring of the vertices of the n-clique-free Henson graph, we can find a monochromatic subcopy in 0 double jump. And it's basically, you know, either there exists some node such that for all the ones above it, blah, 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 or the other way around, and you can then build your subcopy with one color. In our paper, which this talk is based on, which hopefully will come out in a couple weeks, everything's written up, we're just proofreading. We can improve this to zero jump, and the way that that goes is by using that tree structure that I showed you before in order to reduce the zero double. This comes after this theorem of Gill, who proved this in his PhD thesis with Linda Westrick, that there's a computable coloring of the vertices. So given n greater or equal 3, there's a computable coloring of the vertices in Hn with no computably enumerable monochromatic subcopy. And this is a big contrast to the rationals in the Rado graph, where you can just by a greedy algorithm get monochromatic subcopies from computably. Okay, so one question that this raises is whether you have cone avoidance for vertex coloring. So given a computable vertex coloring and a non-computable X, is there necessarily a homogeneous copy or monochromatic copy that doesn't compute X? That's open. More reverse math now. So let's let this denote the statement that Hn has finite big Ramsey degrees. A couple years ago, Angles, Doriak, Liu, Minotti, and Pate showed that this statement is provable in ACA not plus. And this is, in a sense, a corollary really of their broader theorem, where they were showing that Carlson-Simpson theorem is provable in ACA not plus. And then they apply a proof of Hubitschka, who used Carlson-Simpson theorem to recover this result, but from a much shorter proof. So one question is whether we can knock off the plus. That's something we're working on with Henry. But we do note that, yeah, this ACA not plus is coming from this theorem of Glass, Heinemann, and Hurst. So in this paper I'm talking about today, we're interested in finding lower bounds for the arithmetic strength of certain big Ramsey degree statements. So we want to do things as simply as possible. So we look for particular expansions or diaries for particular graphs and see what we can do. So we will recall our notion of the expansion of our structure, which is going to give rise to the expanded structures that give you the big Ramsey degrees. And within that, now we're going to talk about neighborhoods. So V0 is kind of on its own. You can kind of just ignore it. N0 is going to be the neighborhood of all of the vertices that have an edge with V0. N1 is going to be the neighborhood of all of the vertices that have an edge with V1. So this going off to the right means it has an edge with V1. And some notation we're going to use here is we're going to let the first index denote the neighborhood it's in, and the second index denote which vertex it is in our linear ordering. That went fast. Okay, there we go. Okay, so a kind of refinement of what goes into Jakish's argument for getting his jumps from this computable coloring for a Ramsey property on the natural numbers is that we don't actually need a full homogeneous subset of the natural numbers or a full infinite set. We just need something that's called largely two extendable. So We'll say that a set of n tuples of a set X is largely too extendable if the set of the first indices is infinite. And there exists an X0 where then there's infinitely many X1s where the first pair is in F. And then giving any member of F, if we fix the first two pairs, we can infinitely much find things above other things to complete into F, right? So it's basically giving you an infinite search, but it's a little bit more restrictive than saying we need a whole full infinite set where we're taking all of its n tuples. And if you have just a largely too extendable set, that is enough to do the Jockish theorem. And so this is going to be used or applied in the later work. Okay, now for anti-clique. So these are very simple to understand. We're going to color anti-cliques inside of some Henson graph. This again is our leftmost path or our stem. So there's no edges along here. And these three nodes are an anti-clique of size 3 because they're both going by this one left here, so there's no edge. And this one's going by here left, so there's no edge. This is one of those expanded structures that you get a big Ramsey degree from. Or in other words, this sort of structure has the Ramsey property inside the expanded structure. So we have far anti-cliques, and we show that the statement that far anti-cliques of K have the Ramsey property inside the n-clique-free Henson graph codes 0 to the 2k minus 2, and then hence it has to imply ACA over RCA naught. So the proof is adapting the Jockish colorings to largely too extendable sets. The reason we want to do that is because we want to anchor that first pair here. We don't want to have to worry about them afterwards and then choose these as large as we want to. A second result in this paper is on closed pairs. So closed pairs are pairs of nodes where the first one, in terms of length, comes off the stem after they've both come off the stem. And if we let G be either an edge or a non-edge, we let FG be the set of all the triples of this first one, the second J0, and this next J1, where this is a copy of G and H3, then we get that this set is largely too extendable in every copy of H. That's the point, because we can have subcopies of H where you have like stubs and they don't look nice, and so you can't, like, you might choose the wrong way. You might choose some path and there's no infinite extension of it, or there might be an infinite extension of it, but it doesn't have the subgraphs that you want. So that's why this largely too extendable thing is important for us. And then from that, we get that these close disconnected pairs or connected pairs have the Ramsey property that codes 0 prime, and hence ACA over RCA. Okay, so close graphs in general now are looking like this. So originally we had wanted to do something a little bit more concrete than this. We had wanted to fix something that I was calling a harp, where you have these nodes all coming off before the first one, and then these nodes growing up like this, right? But there was a problem. We couldn't figure out how to apply the Jockish coloring and get a largely too extendable set for that one particular configuration. So what we did was we allowed these nodes to be any ordering between them, but all above this one. And so that's what we're defining to be a close graph. And this is all in terms of the original enumeration, our original computable enumeration of H. And so using some prior work that tells us that we can have, for every subcopy of Hn, there is a subcopy again, which is going to be largely too extendable. And we know that this is going to be bi-embeddable inside of anything else. Then for every copy of Hn and any k-n click-free graph with at least 2 vertices, there's going to be a family 8f of copies of this graph, which is largely too extendable and important, that's the hard part, importantly computable from the H tilde. And so putting all of this together, we get lower bounds for the colorings of the finite graphs in Hn. So let n be anything greater or equal to 3, and G be a finite k-n click-free graph of size at least 2. Then there's a computable 2 coloring on the set of close copies of G in Hn, so that there is a subgraph where all the close copies have the same color, namely the 1 color and the Jockish coloring. And moreover, then because of the Jockish coloring properties, it's going to compute 0 jump to the size of G minus 1. Okay. So again, what we're doing there is we're using, for the coloring, we're using this node, this node, this node, and this node. And the way we get this in a very concrete way is, you have this extension property of these Henson graphs. So once you have picked this node large enough so that you have some other nodes that are disjoint from each other, you can say, okay, I want this node, I take it. Now I want another node, I want it to be somewhere over here. And I want it to have the edge or non-edge relationship that G has. So you anchor it by saying, okay, I want this to have an edge with that other node over here and the right relationship with this one. And then you want this next one to have the right relations with these two. And you can anchor it below here by taking another independent node that you've fixed this n to be large enough so you have it available. And you can say, okay, by the extension property, we're going to have some node that has an edge with that other node. Problem is, we don't know where this node is compared to this one. We don't know how to do that computably. So what we do is a little bit more general, and we say, given our G, we look at all these close copies, we do our coloring, and then we get this result. So some open problems, things that we would like to have. For each diary delta, for a finite graph G, is there a computable coloring? So this is the expanded structure that has the Ramsey property. Is there a computable coloring of the copies of delta in Hn so that any monochromatic subcopy computes 0 to the k minus 2, where I want k to be the number of levels of delta. So it would force the jump function to grow a lot faster than what we have so far. That relates to this question, whether the arithmetical lower bound function for this statement, is it the same as the Jockish function? Probably not, but that's open. And how rapidly does this function grow as n increases? As n increases, the big Ramsey degrees grow super, super fast. So I really think it should go up as n goes up. And that's it. Thank you.